So welcome to this week's zkStudyClub. Today we have sort of the part 2 of the Halo study clubs that were started last week with Sean. Today we have Daira Hopwood, who's going to be speaking about Halo optimization and constructing graphs of elliptic curves. Take it away.
Hello.
And welcome.
Welcome, everyone. I'm Daira. I'm a cryptographic engineer at Electric Coin Company. There are my usernames, and this is the GitHub repo with the slides and some animations and some code. There's also a bit of code in the Daira/Tweedle repo as well. The outline of the talk, we're going to discuss what a graph of elliptic curves is and why they're useful, and how to construct them. So what are the obstacles to doing that? And it turns out that we'll need a category of curves called curves with complex multiplication. Those make it relatively easy to find cycles. Then we talk about other properties you might want of the curves, like twoadicity, which is useful for certain proving systems, sort of more complex graphs, and hopefully, if the demo gods are with me, then some live coding in Sage Math to show you how to solve part of the problem for some new, arbitrary new curve that you want to construct a cycle for. And then we go on to Halo optimisations, so describing what Halo and sonic circuit model is, how to do scalar multiplication in circuits, how to optimize it even further, and then doing Fiat-Shamir in a circuit. Okay, so let's carry on. So what do I mean by a graph of elliptic curves? We've got, it's a directed graph, so we've got a set of vertices that are going to be the primes defining our fields, so the field of definition of each curve. And then the edges between those primes represent the curves themselves. So we draw an edge from one prime to another, so from P to Q, when the field of definition is FP, and we have an order Q prime order subgroup. So that's FQ is where we're going to be doing the cryptography in the proving system. So yeah. Okay, and we assume that our proof system using this curve can efficiently support circuits over FQ. Okay, so why would we need anything other than a simple 2-cycle? Well, sometimes we want pairing-friendly curves for our proof systems, and so that's a functionality that we wouldn't get just from a simple cycle. So I've drawn the pairing-friendly curves here in green. This on the top left is just a cycle of normal curves that aren't pairing-friendly, as used for Halo. Then below it we have, can you see my pointer, by the way?
We can.
You can. Oh, excellent.
Yes.
So this one is a half pairing cycle. So one of the curves is pairing friendly. And this is something like the cycle in the original BCTV 14 paper, where this could be an MNT4 cycle, MNT4, MNT6. So something like that. And then you've got things like you have one pairing friendly curve, you construct another one on top of it with Cox pinch or whatever construction you want. Or this one here is like we use in sapling. We have pairing-friendly curve like BLS 12381, and then another normal curve called, which is jojub in the case of sapling. And here, this is something a little bit more interesting that I've been working on recently. I don't know whether we're going to need it, but the idea is that you have a halo cycle, and then on top of one of those curves, you have a pairing-friendly curve. So that means that you can, say you wanted to use grot16 to prove something about halo proof, then you could use this kind of construction. And I call this an inverted lollipop just because of the shape and because so we were originally trying to find so the opposite construction where you start with a small curve and then you go up to a cycle, but it turns out that that's very difficult to construct and we don't know how to do it. So this is one thing that you can do instead. Okay, so why do we need cycles?
Daira, could you go back
Mm-hmm.
For this cycle in the middle with the black and the green arrow? Is there an application
that's
for
not
that?
a cycle.
No, sorry, in the left side, the middle of the left side.
Yep.
Is there an application for that? So you have one pairing friendly and one non-pairing.
So this is actually used by the Pickles proving system. I don't know whether we've got Isaac Meckler or I can't see who's on the call, but ask him about this kind of construction and why it's useful. The idea is that you can do succinct proofs within the cycle. So the pairing friendly curve, you could use, say, Plonk or grot16 or something like that. Obviously that comes up with the trade-off that you need a trusted setup for the pairing friendly proof system normally, but it can be useful for efficiency.
Thank you.
There. So when you talked about the inverted lollipops, you mentioned that that was an alternative to something else which didn't work out. What was the other thing?
The other thing would have been you start with a chain of pairing friendly curves, so like we have here, and then with a cycle on top.
Okay.
So it looks like a lollipop.
Thanks.
Okay. And I don't know how to make those. Why do we need cycles? So we assumed that our proof system could directly support arithmetic over FQ, where Q is the prime order. But if we want to do arithmetic with the wrong field, so not FQ, that has an overhead of over 1,000 times. So I worked it out for, say, another 256-bit field, and it's something like 1,200 times. 1,200 constraints in R1CS to do a reduction in the wrong field. And that's explained in this ticket. So we can use something like pluckup, which is a way of doing tables in sort of Plonk-like proof systems. And that does help a lot because we can, how this works, the sum of residues reduction, is you take each bit in the partial product and you reduce it independently and then add them up. So what pluckup allows you to do here is to define tables so you can process more than one bit at once. But the cost of those tables is it's proportional to the table size, so exponential in the table width or the number of bits you're processing at once. So you end up still having a very significant overhead because you can't use very large tables. And for Halo anyway, we want to minimize the cost of the recursion subcircuit. That's part of the aim. but you could use lookup in the same proof system if it was compatible, if you made those changes. So it's going to be a little bit more complicated than just using if you only needed to do one level of recursion, then it would be sufficient to just do your arithmetic for one curve using the scalar field of the other curve. But what we'll actually need for the recursive proofs is to use 2 instances of the proof system. We've got some diagrams of that later. So this is the cycle that's in the Halo paper. It actually takes a few hours to generate, but that's just because we searched for curves with other nice properties besides forming a cycle. So you'll see here that both of these primes, the zeros here mean that it has high periodicity. That's useful for some proving systems. They both have 126-bit security. So they have cubic endomorphisms. So we'll explain what that means later, but it basically means that you can do scalar multiplication more efficiently. And these conditions here mean that the power of 5 map, so the map from x to the 5 in the field, is a permutation, and that's useful for algebraic hashes like rescue. So I'm going to explain how we constructed these and sort of how you can generalize it to other graphs of curves. Notice that these are short Weierstrass curves. So what's the problem with constructing cycles? So we have something called the Hasse bound, which determines what range the order of an elliptic curve can fall into. So if you have a curve over fp, then its order is going to be approximately the same size as p, but it can vary by something that depends on the square root. So if you have a 255-bit curve cycle like Tweedle, then the order of each curve lies in a range that's 2 to the 129.5. So that's obviously a huge range. And there's a conjecture called the Sato-Tate conjecture about how that distribution varies. It's not uniform. It takes this shape here, but we don't need to go into detail about that. The point
so question, this is a bit confusing because it seems like you're suggesting the order is 2 to the 128, roughly speaking, but it's 2 to the 256, right?
No. This is the range in which the order can lie. I'll show you on the next slide. So each of these values is roughly 2 to the 256, but the range of possible orders is a 2 to the 129.5 range. Is that clear?
When you say range,
it's like
minus 2 square root p to up to p plus 2 square root p.
Correct, exactly. Sorry, I probably should have said that explicitly on the slide. Okay, so the point here is that if we start with a curve over fp, we find its order q, and then we construct another curve over fq and find its order r, then there's negligible chance that p will be equal to r, unless we do something else. We use some special construction. Okay, is that clear to everyone? Okay, I'm going to assume it's clear.
This is assuming the field that it's over, correct?
Sorry, what was that? I didn't quite hear.
Oh, I was saying this is assuming the field, like you're not going over extension fields or anything like that.
We're only using prime fields here. I should have clarified that. It turns out that it's difficult to use extension fields. Prime fields are much easier. Anyway, so what if we had some way of constructing curves so that one of the possible orders was guaranteed to coincide? So here we have curves over FP, and they only have 6 possible orders. And then when we go to the curve over FQ, it also has 6 possible orders, and it turns out that one of those orders is P. So when we try to find coefficients for these curves, so remember that the curve equation is y squared equals x cubed plus b. So b is the coefficient here. As we vary b, we will get sort of one of these 6 values, and similarly for the one of these 6 values.
There are only 6 orders if we are restricting ourselves to this equation type, which is a is equal to 0.
Yes, correct. There are 6 orders for any given p, and similarly for any given q. Okay, so it turns out that CM curves, so curves with complex multiplication, have exactly this property. And the case of where there's 6 possible orders is just the case that the equation that I just gave, y squared equals x cubed plus b. So I'm going to try to explain what complex multiplication is without using much heavy-duty number theory, but just to make it less mysterious, and we'll see how well I do.
Sorry, I'm just confused. On the previous slide, you said that if you vary the b, you get 6 possible orders for the curve.
Yep.
And it seems now that you're saying that this property is actually satisfied as soon as you are complex multiplication. Is it always the case, or do you need something else for these 6 orders to be there?
So for complex multiplication curves, you have at most 6 orders, and you actually may have 2, 4, or 6 orders depending on the equation. And for the equation I said, you always have 6 orders.
Yes, I mean, in general, when J invariant is equal to 0, you have 6
yes,
orders.
Exactly. I talk about J invariance a little bit later.
Okay, I'm sorry.
Yeah. Okay. So, so any curve has an endomorphism ring. So I think we've talked about endomorphisms in previous zkStudy clubs, but basically it's a group homomorphism. It preserves the group structure. That's from the curve group onto itself. And you can compose endomorphisms, so you can effectively multiply them by composing them, and you can add them, and there's an identity, so therefore it's a ring. And so an example of this is scalar multiplication by a constant is an endomorphism. You can easily check that. But what you can do is to consider any possible endomorphism of an elliptic curve group as being like a generalized scalar. So normally we're used to scalars being integers, but think of any endomorphism as being a scalar. This is just one possible way of explaining it that I find.
So is an endomorphism a set of homomorphisms?
An endomorphism is a homomorphism that is from the group onto itself. That's the definition. Is that clear?
Kind of. Thank you.
I think the question was about the endomorphism ring being a set of endomorphisms.
Yes, yes.
Oh, sorry. Yeah, it's an algebraic structure. It's a ring of endomorphisms. So each element in the ring is an endomorphism.
I see. That's a bit harder to imagine. That's why. Okay.
Okay. Well, if you consider the simple case where you just have integers, then it's clear that it's a ring, right? And then the elements are just elements of the ring. So the ring is just Zn, where n is the group order. Is that clear?
Yeah.
Okay. Right. So if we were just considering elliptic curves over finite fields, then it turns out that all endomorphisms are equivalent to scalar multiplication by an integer. But for any curve over a finite field, we can consider the curve with the same equation over the complex numbers. So each coordinate is a complex number. So it's a little bit hard to visualize because you effectively have 4 dimensions, 2 for each coordinate. And then complex multiplication just means that you can scalar multiply by a complex number. So here's an example. We have this elliptic curve, and we define multiplication by I, so I is the square root of 1, as this. You check that it works. So if you apply this map twice, then you get x here, then minus y, which is the same as I squared times xy. So it works. So what you end up with here is the scalars are elements of a complex lattice. And in this example, the lattice is Zi. So that's, I'll show you some pictures on the next slide, but that's just the Gaussian integers of this. And if I've lost anyone, then it's going to get simpler when we just consider the case of finite fields. So don't worry about it. I'm just trying to make the idea of complex multiplication less mysterious, because it's referenced very often in papers, and they don't explain it at all. They refer you to Silverman's book or whatever. And it is actually reasonably easy to explain, sort of just using basic principles. Okay. So we said that these generalized scalars, so these endomorphisms, are in a complex lattice. So here's the example we saw on the previous slide, where the elements of the lattice are in this arrangement. So this is called the Gaussian integers. And the other case, which is the j equals 0 case that we're interested in, these are called the Eisenstein integers. So here, so if you have 4 units here, which are in the lattice, and here the green dots here are the units, so you have 6 on the unit circle. So that's what defines these lattices. So this case is nice for cryptography, and sec P256K1 falls into this case. So we're not doing anything especially controversial or new here, because the billions of dollars riding on sec P256K1 being secure. Okay, so I just told you about the units. They're the elements that have a multiplicative inverse. So if you take some other element here, say this one, that doesn't have an inverse in the lattice. It's only these that have inverses. So the inverse of 1 is 1, for example. And it turns out that the orders correspond to the number of units. So if you have a lattice like this, then you'll have 4 possible orders of the elliptic curve. If you have a lattice like this, you have 6 orders. So that's why that happens. And then when you map from the elliptic curve over... sorry, I didn't quite hear you there. Your sound was difficult to understand. Can you say that again?
I think that person just joined, actually. I think it was just some background noise.
Oh, okay, no problem.
Yeah.
Okay, so when we move from the elliptic curve over the complex numbers to the one over finite fields, these complex roots can correspond to roots of unity in the finite field. So we might have so 6 roots of unity in the finite field, and then it will turn out that multiplying by one of these scalars is equivalent to multiplying by an integer. But it will be a shortcut to multiplying by that integer because sort of moving sort of in the imaginary direction here in the lattice. Was that a question?
I don't think so. I think it was
okay.
Background noise.
So moving to one of those units corresponds to applying an endomorphism, which can be quite easy to compute. So that's useful. Okay.
So Daira, what do you mean? So just to see, I understand the notation. EP arrow Q means the whatever they're called, isogeny, whatever they're called.
No. This is just saying that we have a curve defined over FP, and its prime order is Q.
Oh, so that's just the endomorphisms of this curve.
Sorry. Yeah. So in the finite field case, the endomorphisms are just the endomorphism ring is just the integers.
I'm saying this notation is EP arrow Q is for the endomorphisms of this curve of like size P over FQ.
You can think of it that way, yeah. You can just think of this as being the field of definition P and the scalar field Q if you want. Because after we've explained complex multiplication, we're just going to go back to considering the simpler case.
And what is you say the units correspond to the possible order? What does it mean in order of EP arrow Q?
Oh, sorry. The possible orders of EP as you vary the coefficient B. And the number of those.
The possible, the units of L correspond. I see, and you haven't said how this correspondence happens.
Yeah, I will get to that.
Okay, cool. Yeah, no, I thought it was like order in the sense that sometimes they talk in complex multiplication.
The problem with number theory in general is having too few words in English to describe the number of concepts.
Yeah. Okay, thanks.
That's
the only problem with number theory. No other problem.
Everything else is simple. Notice how I carefully avoided saying unit circle here because that would have been really confusing. Okay, so we should consider whether CM curves are secure. I mean, I've just said that SecP256K1 is a CM curve, and all pairing-friendly curve constructions that I know of, or that are in any papers I know of, produce CM curves. So this is a very well studied thing. And I don't think that there's any reason to believe that the discrete log problem on these curves would be any less hard. Okay. Even though they're only a small fraction of curves. Okay, so when we map the CM curve back to the finite field, it has a small number of possible orders determined by the number of units, and that's determined by the J invariant. So turns out this case here, where we have a Gaussian lattice, is J equals 1728. And this case here is J equals 0. And you can compute the J invariant just based on the curve equation. I'm not going into how you do that, you can just look it up here. And the reason why J invariant 0 curves are interesting is they have 6 possible orders, and it'll turn out that it's useful to have sort of several possibilities for the order, because sometimes some of them are excluded because they will never be prime. So you basically have 6 bites of the cherry to get something that's prime.
Are these 6 possible orders explicit, or do you have to?
Yeah, so I'm going to go into that in a few slides, but basically there's something called the norm equation, which allows you to compute them explicitly. We're going to go into some detail on that. Okay, so this is the norm equation. dv squared equals 4p minus t squared. So all of these are integers. This d here is called the fundamental discriminant, and by convention it's normally negative. So what I've done here is just take the absolute value, and v, obviously p and t are integers, and then you have a trace t. So I'm not sure how many people are familiar with sort of the enough elliptic curve cryptography to have seen this before, but the trace is basically it determines the difference of the order from p plus 1. So remember we talked about the Hasse bound. So the range of possible q's is p plus 1 plus or minus 2 root p. So that range, and then t here is something that can vary up to 2 root p in magnitude. And then it turns out that there's a relation between this t, this capital T, and the trace. So plus or minus t are 2 of the possible traces. And that's the case regardless of the J invariant. But in some cases, there might be more possible traces than this. So for the Tweedle curves, all we do is set d equals 3. It turns out that for CM curves, where the order is prime, d will always be 3. And then we can almost freely choose integers v and t. And then from that, we can compute the prime. So we can both the prime and the order, actually. And the reason we want to do it that way is we want both of the curves in the cycle to have high two-adicity. And we'll see in a minute how we can choose v and t, so that's always the case. But first of all, this is an explanation of why this property holds. So there's a proof by Stanger and Silverman But their proof is quite complicated. And so I wrote up a simpler proof, and that's in the accompanying notes, which are in the GitHub repo. So the proof actually of the case that we use for Tweedle fits on one slide. And so we have this norm equation. And we want to show that one of the possible orders for EQ is P. And it's just a straightforward application of algebra. We end up with, so we have to distinguish between the V and T for the curve over EP and the V and T for the curve over EQ. It turns out that the V is the same for both, but T is different. So TQ will differ from TP by 2. And if it does, then it works out that the order of EQ is P. So this is one of the possible orders of EQ. And remember, we're going to have to search for the coefficient that gives this order. So is that reasonably clear? This is just to explain that there's nothing mysterious about why this should happen. It's something
so
right out in the
slide. Can we recap real quickly what happened up until this point in the presentation? Because I'm a bit lost as to this whole CM.
Oh, okay. So what we're trying to do is understand the construction for creating 2 cycles of curves. So curves where the order of one is the prime over which the other is defined.
But non-pairing friendly?
So this is in general. So both for pairing friendly and non-pairing friendly curves.
I see. Okay.
So any CM curve. Pairing friendly curves are basically CM curves because that's the only way we know how to construct them. But you can also construct non-pairing friendly curves that is CM. Sec v256k1 being an example.
Hey, Daira, this might be a good moment to have a quick peek at the chat. I don't know if you can see it on your screen easily. There's a few points that were made, so it might just be worth it to check it out quick. And if anyone else has anything they want to kind of raise, this might be a good moment to do that too.
I don't seem to be able to see the chat without stopping screen sharing for some reason. I don't understand why that is. Can you just read out the questions in the chat and I'll answer them?
So
just go ahead.
Youssef, do you want to say what you wrote because it's a bit longer than just a question?
No, I just didn't want to interrupt because maybe it's not that important. But in one slide you said that so the ring of endomorphism is equivalent to the scalar multiplication by integers when we are talking about elliptic curves over finite field.
Yeah.
Why I wanted to say it is the case for ordinary elliptic curves, because for super singular elliptic curves, the ring of endomorphism is an order in quaternion algebra, so it's not multiplication by scalars. But I just didn't want to interrupt you for this.
Thank you for the correction. I'll correct the slides there. Yes, we don't want to use super singular curves because they're insecure. But yes, that point is well taken. Thank you. Anything else from the chat?
I think everything else was like additional ideas or kind of backing up some of the stuff that was being spoken about. And someone did ask if I would export this. So what I usually do is I take kind of relevant links and I add that into the show notes of YouTube. But if maybe I can add some of this text as well, if you guys think that would be useful.
So there is there are some notes which are on HackMD. Let me actually
I think you already, did you already share that in the group before?
I think I did, yeah.
Okay.
Yeah,
We'll put
I'm pretty
this-
sure I shared them.
We can put this, we can share it in the group after, and we can also put this on the YouTube chat as well.
Cool. So, yes.
I do actually have a question.
Go
on. So safe curves makes a big deal about low CM discriminant enabling some sort of row speed up. Is that a concern here? Is that why we're looking for 130-bit curves? Does it matter at all?
You can compute exactly the speed up. There's a footnote in the Halo paper about exactly this point. So yes, you can use the endomorphism in Pollard row, and that gives you a speed up of I think it's square root 3 or something like that. So it's barely significant, and you can just compute what security your curve has, taking that into account.
Yes, I think that it is well known, but when people are talking about the discriminant, the complex multiplication discriminant being small, it's not about the security, but it's about the complex multiplication theory gives you the existence of the curve, but then you need to find the coefficient A and B in short-wave transform, for instance. So if the discriminant is too big, then you cannot find this coefficient. There is a method by Atkin and Moran to find this. But in the kind of curves Daira is talking about, when the J invariant is 0 and when you have just x cubed plus b, you do not need this method because you have only 6 orders. You can just try a few coefficients until you the one clicks.
Exactly. Yes.
Okay. Thank you.
Yeah, that was a good point. Thank you. So we want both curves to have high two-adicity. Typically, we want, so if we're using, say, Grot 16 or BCTV 14 proving systems, then we would need a two-adicity that depends on the circuit size. So a two-adicity of C would allow for a circuit with 2 to the C gates. And the details may depend on the proving system, but that's the basic idea. So we want both P and Q to be 1 mod 2 to the C. And here's how we do that. I'm not going to sort of go through this in detail, but the idea is that we can freely choose V and T, so we can choose them in order to guarantee that both P minus 1 and Q minus 1 are multiples of 2 to the C. And this actually only works for 2 of the possible orders, so 2 of the 6 orders, but that's okay. So that's basically everything for Halo cycles, but we might also want cycles that involve pairing-friendly curves. Just so that we can use a greater variety of proof systems. So brief recap of what a pairing is. It's a bilinear map. I'm not going to go through this in much, take too long on this. So we pick our pairing friendly curve. We're going to assume that it's in a parameterized family. So we have an integer parameter x, and then P and Q. So P is the field, FP is the field of definition, FQ is the scalar field. They're defined by these polynomials in X. So BN curves are an example here, Burito-Neri curves. And so are BLS and KSS and MT curves. Any curve construction that you might want to use in cryptography is of this form, really. So let's consider how to make half pairing cycles. So I already answered this in response to a question before, but the reason why you would want these is so that you can you can use a proving system that produces fully succinct proofs as part of the cycle. So you won't be able to use that for both sides of the cycle, but only being able to do it for one is sometimes sufficient, depending on the sort of exactly how you do the recursion. So I think Isaac Meckler has a video about the pickles proof system that explains sort of how that uses them. So in order for curves to form a cycle, they have to be prime order, so that the orders are within each curve's Hasse interval. And so that restricts us to some families of pairing-friendly curves like BN, Freeman, or MNT. And in practice, we want the curve to be as small as possible for a given level of security. So we want BN curves. And it turns out to be trivial because all BN curves will form a cycle, a two cycle. So we just search for the coefficients. That's just a consequence of this. Okay. And to get the two-adicity, we just choose the parameter to be a multiple of whatever two-adicity we want.
But if all BM curves form a cycle, they're pairing friendly, so you get a full pairing cycle, not a half pairing cycle?
No, the other curve will have very high embedding degree, so it won't be pairing friendly.
Okay.
Yeah.
And I think you can't get cycles of pairing friendly curves with BN by definition.
Yeah, that was proven in I can't remember the authors, but
yes, Chiesa and Shura paper. Yeah.
Yeah. Yeah. And it also proves it for Freeman curves as well.
Yes. I mean the basic proof is just a sum of the traces. The sum of the traces is equal to the number of cycles. So in BN curves, for example, the trace is 6 times x squared plus 1. So if you sum these equal to 2, then you will have the only solution is x is equal to 1. And x is equal to 1, then you cannot find a prime order for P, neither for Q.
Yep, exactly. Thank you. So, yep, choosing x here. Notice that if x is multiple of 2 to the c, then so are all of these terms that involve x. And so you get 1 modulo 2 to the c. So we might want to have other constructions with one pairing-friendly curve in the graph. I don't know how to do constructions with 2 pairing-friendly curves unless you use something like Cox-Pinch. So anyway, if you have one pairing-friendly curve, then just figure out what your polynomials are for P and Q here. So you need to solve the norm equation that I gave before for each of the other curves in the graph. And so if it's not obvious how to solve them, you can sort of just construct some in Sage, say, find its order, and then work out from that what the solution to the norm equation must be. So J equals 0 curves, so very convenient here because we have 6 chances to find a prime order. And then just to optimize the search, we can work out sort of congruence relation on X so that all of these polynomials are more likely to be prime and to have the right. You can't always produce curves with high 2-adicity. You might have to settle for high 3-adicity or some other small value of Z. So let's see whether we can give an example of that, of solving the norm equation. So I'm going to have to stop screen sharing the slides, and I'm going to a Sage window, and we'll see how to do that. So the motivation here is we want to construct a KSS 18 curve, because this is the smallest construction I know of, the construction that gives the smallest p that I know of. So this cycle has to be around, sort of Q and R have to be around 256 bits for security. And then KSS 18 will give you a secure pairing, because the size of GT will be 345 times 18, which is 6,100 and something. So that's secure, but this is minimal. So let's, okay, stop screen sharing, and I'll screen share my Sage window. If I can find it. I guess I should have closed most of my windows in order to make this easier.
Just reboot the whole machine.
Ivan, you had that question in the group. Did you feel like it got answered?
Yeah, I think so.
Okay, cool.
Okay, cool. So do you see my screen?
Yep.
Yes.
Okay, cool. Let me just put my notes. Okay, so the first thing we need to do is to work out the polynomial for the order of the curve, our pairing-friendly curve. Won't bother looking at that up because I've got it in my notes. We have this is a slightly different parameterization than the one you usually see, and the reason is that the usual one doesn't always produce integers, but this is equivalent. So it's 343 u to the 6 plus 37 u to the 3 plus 1. Okay. So that's the.
It's for KSS 18 curves.
Yeah. So this is the prime order of a KSS 18 curve. So reparameterizing so that this is always an integer. And then, okay, so we want to choose a u so that this is prime. And we also want u to be quite simple, because we want to be able to recognize sort of the order in terms of u. So what I'll do is prime. So what I'm doing here is checking for each k up to 100 whether p of 2 to the k is prime. I suppose I could just write 2 to the k here, but it's a micro optimization. Why didn't that work?
Don't you mean in and not equals?
It should be in range.
Yeah, thank you. That shows you that I'm not just copying and pasting. Okay, so this tells us, for example, that u equals 2 to the 33 gives us a prime. So if we were actually trying to construct a KSS 18 curve, we would also have to check that so the prime for the field of definition is also a prime, but and it turns out it isn't for this, but it doesn't matter if we're just trying to solve the norm equation, because we're actually trying to find the curve underneath the KSS 18 curve. Okay, so let's calculate our prime P. This is what it is in binary, so you can see it's very sparse. And let's construct our elliptic curve over that prime. And so here are the Weierstrass coefficients. A is 0, B is 5, say, and we'll count the number of points. That was fast. Point counting used to be slow, but not anymore. Sometimes you have to convert things to Python integers in Sage. So let's see what that order is. Okay, it's this. Well, that's interesting because it's very similar to P. So
is P prime, by the way?
Yes.
Can we just check?
I mean, I checked it above.
Okay, because I'm sorry. Because this is the polynomial of KSS 18.
Yeah. Oh, sorry. It's the order of a KSS 18 curve.
Okay.
Yeah.
Okay.
So all we need for this exercise is that the order is prime. If we were actually constructing the curve, we would need the field of definition to be prime as well.
Daira,
yes.
is there a reason that we're restricting attention to prime order curves? Isn't it okay if it's just has a large prime factor?
So
actually, the prime you're talking about, I think, is the subgroup, the prime subgroup order of the prime friendly.
Yes,
curve, right?
yeah. So exactly. KSS 18 curves are not prime order. So you also have another polynomial for the cofactor, which I haven't bothered with here.
Okay, great. Thank you.
Yeah. So this is just the prime subgroup, which is what we want for to construct our graph.
That makes sense.
Okay. And then, so let's compute what the trace might be. Okay. What's that in binary? Oh, that's interesting. So remember that our parameter was this. Okay, so it looks like this trace might be something like so what's this? Might be 17u cubed, something like that. Yep. Oh, hang on, you need a +1 there. Okay, so let's guess that T is that. So we then have, so remember our norm equation is this. Okay. Well, we have P and we have T, so we can just compute dV squared. Let's take its square free part. Did I take that correctly? Okay, 3. Okay, so d equals 3. That's good. So v squared equals v squared over d. Well, that's a better v square. Yes, it is. So we can take its square root. Let's okay. And so we also need to work out what this is as a function of u. So I think it's fairly clear that this only differs in the first 5 bits here. So it's going to be of the form something times u cubed plus 1. So it's going to be 19. Okay. Excellent. So that's our solution. So let's, okay. Well, we haven't checked that this is true for all possible u, but let's see, we can, I prefer to use Parry for operations on polynomials. So you can do, okay, so this is the polynomial for P. And then V. And then T. And okay, so this is the right-hand side of our norm equation. And then the left-hand side is going to be 3 times VU squared. And it's the same. So we know that this is true for all u. Any questions? So this is basic. So this is not unrealistic because this is actually how I did it when I was trying to write the code to find cycles under KSS 18.
I think people are mostly just really excited to see you live coding. So that seems to
Oh,
be the
yes.
chatter right now.
Cool. I didn't know whether that would all work, but that worked out very well. Does anyone have any questions about the maths? Does anyone think that they could do this for another curve type now? Because that's my goal, really. I don't want to be the only person doing this.
Olivier, do you have a question?
So what is your goal there again?
To teach other people to be able to find arbitrary graphs of elliptic curves.
But the only use case for the time being is something like, so for cycles with pair infinity, at least one of them is pickles, right?
So that slide that I showed only considers that case, but other people may have more ideas than I've had. So
yeah,
you can sort of build on these techniques to do more interesting things, or at least more complicated things.
The reason that this is possible to do with these parameterized families is because we have is we know how to go from a subgroup order to the full curve construction. But could you also do this with something like an Edwards curve?
So an Edwards curve is never prime order, but as long as your graph doesn't require it to be prime order, then yes.
Well, but so in this case with the KSS 18 curves, they're also not prime order, you said.
That's correct. Yeah.
But we simply know how to search for them on the basis of their prime order subgroup, which is
correct,
not necessarily
yes.
true for other curve families.
Yeah, I don't know how you would do it for cases where the order is not parameterized. Because if any of the curves is not CM, then you're not going to be able to solve its norm equation, and so it can still be a leaf in the graph, but you're not going to be able to make it participate in a cycle.
Got it.
Hey, Daira, you know how you have a second half of this talk that talks about the circuits and stuff?
Yeah.
Since we've done an hour so far, did you want to split that into a different study club, maybe?
It's a shorter part of the presentation. Let's see. I'm on slide 23, and it goes up to slide 36. So it's about half the length of what I've done so far. And remember, I did the live coding bit, so that's also that also took longer. So Anna, do you think we should split it, or?
Well, we have. So I think we could probably do another 20 minutes, but I don't know that we can do much more. So it depends. Do you think that there'd be a lot of?
No, it can fit in 20 minutes.
Yeah?
Yeah,
okay.
I've done this in 20 minutes. Okay,
cool.
So let me...
Just before you move on.
Go on.
Yeah, I was just wondering, so you, I basically have two questions. So you quoted this result that said that you could move back and forth between two primes if you had complex multiplication, I guess.
Yep.
So the first question I have is basically, is this all this paper says, or does it describe other paths you could take between curves? And
so the original Stanger and Silverman paper.
Yeah.
I hope I'm pronouncing Stanger properly. I'm not sure whether it's that or Stanger. Anyway, so what that's trying to do is to count the number of curves that form cycles. The paper's a few years old now, and it wasn't specifically oriented towards cryptography. It was more of a pure number theory paper. There may be other tidbits from that paper that we could mine, but I'm not sure there's anything that's directly useful. Does that answer the question?
Well, I'll just take a look myself, I guess. And the other question I had was, so you said you were going to, you did everything you did as far as I understood it, always with J invariant 0, and you had reasons for it, which I don't remember, but you had on your slide, you said it's better to do it with J equals 0. Do you have any idea if other J invariants would be useful?
So we know that J invariant 1728 never produces prime order curves. That's proven in one of the papers that I referenced. But other J invariants might be useful, yes.
Okay, thanks.
Cool. So I'm going to screen share again now. Start from current slide. And let's see if I can get the Zoom window.
Daira, I do wonder, are you sure you don't want to maybe do like a bonus session where we finish it? The reason I say that is we only have 15 minutes left, and I feel like no one will really be able to ask questions on what you're doing, and I feel like there will be. Also, there's a few people that have dropped off that I think might want to have
all right.
been there. Would that
yes,
be okay?
We'll split it there.
Okay, because I think this is a cool stopping point, and actually
yes,
maybe it's good. We get actually a little bit more conversation out of this. Okay, so let me just conclude, or do you want to say sort of a conclusion?
Well, were there any more questions on the curve construction part?
Yeah, I had a question in the chat. It's somewhat abstract though. Like, you said that it's infeasible basically to find any cycles in non-CM curves, but is there any reason why we would want to do that?
So if you were worried about the security of CM curves, then you might. Other than that,
you might want complete curve equations that are really efficient.
Yeah, if you are to another curve type for legacy reasons, like constructing bulletproof cycles around ECDSA standards or something.
Right, because most of the existing standards, with the exception of SecP 256K1 and some of the other SecP curves, would not be CM.
All right, thank you.
But you can use non-CM curves at the leaves of the graph. Any other questions, or shall we stop recording?
Oh, I just had a quick question, Daira, about requiring the J invariant to be 0. Is there a write-up of that somewhere, or is that in one of the papers you looked at? Or I know you said that's used for the curve used in Bitcoin, so I was just curious, like, where that write-up is of where it's useful.
The main reason it's useful is that you have these endomorphisms. So that's how the second part of the talk followed on from the first. I actually used the endomorphisms to explain how we optimize Halo. So you have to wait for the next part of the talk for me to explain that, I think.
Got it. Okay.
And I think you can also make the pairing faster because you can compress G2 up to a 6.
Oh yeah, that's another good reason.
Mm-hmm.
So that doesn't apply to the Halo curves, but it does apply to pairing-friendly curves.
Yes.
Go on, G-Tang.
But the reasoning about J invariant 0 curves mapping into finite fields in the way that they do is written down somewhere, right? What is that from?
So that is so slide 15. There's a reference to on orders of elliptic curves over finite fields. I think it's in that one. Cool. Yeah, this was fun. It worked out really well.
For your curve search, is your curve search repo the best place to find this? And the second question is the stuff that you did with the parry calculator. Is that part of the like your normal workflow? Is that what you kind of normally do? And you run it on your machine?
Yeah. So my normal workflow is to have a Sage window open and a parry window open, and to just use whichever one is most convenient, because parry tends to handle polynomials with a very sort of simple and concise syntax, whereas for Sage you need to declare the variables. It's slightly annoying.
And for the brute forcing part, can your normal computer handle it, or do you send it away to the cloud and crunch it there? Or?
So my computer can handle it. It's just an ordinary desktop with 6 cores.
Awesome.
and it doesn't. These searches don't require very much memory. Yeah, any desktop should be able to handle it. So how long a search will take depends on basically how much time you have to optimize it, and whether you're searching for any special properties of the curves beyond the fact that they form a cycle. Also, it depends on how many curves you need to check a prime. So by the prime number theorem, so the probability, roughly speaking, the probability of any n-bit number being prime is 1 over, so proportional to 1 over n. And so the larger the numbers are, the less likely they are to be prime. And then if you have to check several numbers for being prime, you have to check more of the parameter space in order to find one. Whereas it's usually, so if you're finding that that is a problem, then there's a trick that you can use, which I didn't put on the slides, but there's a technique called a factor wheel, which you can generalize to use in these searches. So you can have effectively a very large virtual factor wheel that satisfies all of the congruences that you need. So that makes it more likely that that each polynomial will produce a prime. So if you're having trouble with how long the searches are taking, you can use that technique.
No, thank you. I was going to play with it. I just want to make sure that I could. So perfect. Thanks for your talk.
Yeah. So the programs in the curve search repo, they all produce curves sort of relatively frequently. So it's only if you're searching for something very specific that it would take a long time. It takes, I think it's a couple of hours to search for the Tweedle curves, but that's just because we insisted on them being twist secure for some reason, even though we're not actually using twist security in Halo. But anyway. Cool. So let's stop recording if I can find the
Yeah,
window.
well, first let's say thank you. Thank you so much for doing this.
Thank you.
You're welcome. It was a lot of fun.
Yeah, and we'll do a bonus, I guess. After this, we'll organize this bonus edition of the Halo.
Yeah, and maybe I can expand on that part of it.
Cool. Nice.
See you next week, probably.
Yeah, I think something like similar time, but we'll coordinate in the chat.
Okay.
Thanks, everybody.
Bye bye.
Thank you.
All right.